Hello everyone. In this video I will show how to apply loads to nodes and elements. To start with nodal loads, I have to create a node to open the auxiliary dialog window for applying loads. In this window you can select a node by its ID number from the drop-down list, or you can write in this text box the IDs of multiple nodes to apply the load components. When you leave the cursor over the text box, a tip appears to show the input format. Then you can provide the values of the forces and moments. As usual, only the degrees of freedom handled by the selected model type are enabled. F stands for force and M for moments. So in this case of a 2D frame, Fx and Fy are the forces in global x and y directions, which are the horizontal and vertical directions in 2D. And z is the moment around the global z direction, which is the out of plane direction, and it is the only rotation component in 2D. After providing the load values, you need to click the apply button to validate the modifications. And to remove the loads, you just have to prescribe new components for forces and moments. To show how to add element loads, I need to have at least one element created, and I'll also activate the option to display the element orientation. In the window of element loads, as with nodal loads, you can select elements either by picking a single ID from the drop-down list or by writing the IDs in the text box. Then there are three types of loads that can be provided to an element. One is the uniformly distributed force, in which the force components are constant along the length of the element. You can specify if the force components are provided in the global or local direction, and you have to provide these components according to the selected model type. In 2D models, only the x and y components exist. So if I apply a positive force in the global y direction, that is the vertical direction, it will be decomposed into a transversal component in the local y direction with a value of 8.5 and an axial component in the local x direction with a value of 5.3. In the model, loads are always represented in the local directions, and that's why global loads are decomposed. Now, if I change this load to be applied in the local direction, you see that it has only one transversal component with the value of 10. Next is the linearly distributed force. The force components in this case have different values at the initial and final nodes, and the distribution varies linearly between them along the length of the element. Again, you can specify the direction in which you are applying the load components. I will set as local, and the force components in each direction have two fields. The number 1 is for the force value at the initial node, and the number 2 is for the final node. The uniform and linear force components are added, and they are displayed in the model as merged components in local directions. So if I apply a linear force that varies from 0 to minus 10 in the local y direction, together with the uniform force that I had previously applied, the result is a triangular force from 10 to 0. The third type of load is the thermal load, which are temperature variations and gradients. The direction in this case does not need to be specified because all the components are considered to be provided in the local direction. The first component, delta Tx, is the temperature variation of the element along its center of gravity. It affects the length of the element, so it generates axial internal forces. The other two components are related to the temperature gradient between the bottom and the top faces of the cross-section, and they can cause the bending of the element. So delta Ty is the difference of temperature between the bottom face and the top face of the cross-section, where the bottom and top are relative to the local y direction of the element. A positive value means that the bottom face is hotter than the top. This is indicated by the red color at the bottom and blue at the top. A negative value will show that the bottom is colder than the top. The same for delta Tz, but in this case the bottom and top faces are relative to the local z direction of the element, so it's not used in 2D. Just like other conditions, when you click a node or element, their load components can be checked and edited through the addition table. Now I want to show the application of nodal loads in dynamic analysis, as it has a few differences. So here I have the analysis type changed to dynamic, and I have also created some time functions. Notice that element loads are not currently available for dynamic analysis. In the auxiliary window of nodal loads, you have the same force and moment components, but in addition you can provide a concentrated mass and a time function for the loads. In the node specification, when you choose to select multiple nodes, you can also choose what you want to apply to all the selected nodes. If it is everything that is being set in this window, if it is only the load components that are being provided, or if it is only the time function that is being selected. The time function can be selected from this drop-down that lists all the created time functions. When you select one, it shows in the graph the variation of the function, where the y-axis is the amplitude and the x-axis is the time. This function tells how the load, including all the components, evolves in time. So an amplitude of 1 corresponds to the load values provided here, and an amplitude of -1 means that the load components are acting in the opposite directions with these same values. Finally, the concentrated mass is not affected by the time function, as it has the same value at all times, and it represents a point mass that contributes to the translational inertia of the node, but not to the rotational inertia. And with that, we come to the end of this tutorial.